So this is the third lecture. In this lecture, we're going to start talking about how to grade retention systems. This is, again, the third lecture. There will be a fourth lecture to give you more detail. In this lecture, we're going to talk about the actual drawing of contours, labeling of contours, labeling of high points, low points, raised drop inlets, and curb cuts. All of these are things you're going to need in order to grade these systems. Now, we've already talked about how you take a system and cut it into multiple smaller sections. That you've already accomplished. Now we're going to talk about what do you actually do in the bioretention systems. What do you do for the actual curb cuts? What do you do for raised drop inlets if you have them? And what do you do for regular drop inlets if you need those as well? So this is an example of the sort of plan that you're going to have to create. And the basic idea is that you want to create these bioretention systems that are downhill from your paved areas. All of your paved areas are going to need some sort of a system to capture the water. On the other side, you're going to have to come down past the drop-off area. And then one of the things that we are going to have to discuss in greater detail later is how we do these bioretention systems that are located next to a hill, because this hill is going to be pushing water into the bioretention systems. So we're going to have to create an intercepting swale there. The plan that I'm showing you does not have that. One of the things that's incorrect about this plan that I want to point out to you. But we're going to go through all of these so you can understand these as you start to grade your plans. So we're going to start with a very simple example of grading a bioretention system. Here we have a plan that shows the existing contours. We know that the slope is going downhill. We don't know the percent slope, but we can assume it's about 2%. And what we're going to do is we're going to talk about how we're going to then come in and modify this plan so that we can create basically a hole in the ground that will hold water. So the first thing we want to do is very simple. We want to take these contours and push them so that we have a flat area in the middle. This flat area then we're going to excavate out so that we can hold water in it. Now, when we put in these new contours, it's important that you understand that this contour, the very first contour that goes in, is the same elevation as the contour that is right below it. So this is a 6 contour as it's labeled, and this is a 6 contour as it's labeled. That means that both of these are 6 contours. This and that are both 6 contours. The reason that we do that is that eventually we're going to need to create high points here so that in all honesty, we're creating a berm that goes below our retaining area. Water will then flow into the retaining area. It will fill up with water, but water will not overflow down the hill because we've created a berm or a dam, if you will, right across here. We're going to talk in more detail about how we're going to specify that and also how we're going to create a raised drop inlet so that water does not overflow. So now we have added the high points and the low points. And yes, you must actually label them with an HP for the high point and an LP for the low point. What we've done with these high points is we have basically created a berm here along the downhill side of the system. So again, water is going to flow in to the system. And then the low points will determine the bottom of the system. You generally want to have more than one low point, so you spread the water out as much as possible. You'll also notice that the depth that we have for this system, because we've got a 4.5 and a 6.5, is about 2 feet, but we're going to make some adjustments to that in a minute. So the way we control the depth of the water sitting in the retention system is with a raised drop inlet. And you'll notice that this raised drop inlet is half a foot below the high points on the berm. That's important. You have to maintain that half a foot below. And the reason is that when these things are constructed, construction is not always perfectly accurate. And you want to make sure that your raised drop inlet is not just a tad below, but actually half a foot below the berm that you have shown on the downhill side. What will happen then, of course, is that water will run into the system as it did before. The system will fill up with water. And when it gets to the elevation of the raised drop inlet, then the water will simply flow into the raised drop inlet and not flow downhill over the berm. That's very important, that we not allow the water to overflow the system and erode the bank. We want the system to be used so that the water overflows into the raised drop inlet. Now we've added a parking lot, and that parking lot is just right up against the bioretention system. We basically have water flowing towards the curb. And the thing that students often have difficulty understanding is what happens to these contours that are on the back side of the curb. That is in this area over here on the back side of the curb. So to start with, let's talk about what happens to the ones as they come out from the parking lot. So this number 5, for example, it's going to come down, it's going to come across. It may well then run on the back of that curb and then over. And I want to emphasize that point, that it can run on the back side of the curb there, because what we're going to do is we're going to lower the landscape areas so that they are actually lower than your parking lot, and that allows water to drain into them. So then if we look at number 6, it's going to run down, along, over, and then run off by itself. This other 6, though, this other 6 that we added, it's going to run along the back side of the curb and connect into itself. So that 6 is running along the back side of the curb and connecting into itself. And this 5 is actually running around, and it's going on the back side of the curb and connecting into itself. So what that means is that in this area where we have the bioretention system right next to the curb, the depth of the bioretention system is further down on the back side of the curb than the asphalt is on the front side of the curb. In fact, in this case, it's about a 2-foot drop. So we'd have about 2 feet of the back of the curb exposed to the bioretention system. So for all intents and purposes, that curb becomes a retaining wall. Likewise, the 7, it might come across, run down, cross over, and it's also going to run up along the backside of the curb and then off. And then the 8 will do the exact same thing. But again, I want to point out to you that the backside of the curb, you can have contours stacked on the backside of the curb just as if it was a retaining wall. This is very important for you to understand before you go forward. One of the things that I often do is I might actually trace these contours in different colors and actually have a little bit of space right behind the curb where I let those contours stack up just so I can see them right now and I don't forget where they're located. So let's clean this up and go over it again, because it's an important point that we need you to understand. Your 5 contour is just going to run across the parking lot. It's going to then run along the face of the curb, cross over, attach into the 5, and go off just as it did before. The 6 contour, same thing, runs across the parking lot, comes down, crosses over the curb, and attaches into the 6 as needed. Now, what's important to know here is that the second 6 contour, and you have to have that second 6 contour, it connects to itself and it runs right along the face of the curb. The 5 contour does the same thing, connects to itself, and on the back face of the curb, it simply connects in as well. So it's important to recognize that we have a 2-foot difference in elevation between the front side of the curb and the back side of the curb. That allows you to sink your landscape areas as much as you need to get them to hold the water that you need. And then obviously the 7 does the same thing, runs across, over, connects back into the 7, goes off as that needs to into the landscape area, and of course the 8 does the same thing as well. This is a slide you should probably come back to a few times to make sure that you understand how we're able to run these contours along the back side of that curb in order to get the depth that you need to hold the water in your landscape area. So now we've added a curb cut here, abbreviation CC. It's not a standard in the profession yet, but it's what we'll be using for this class. We need to talk about where you choose to place your curb cuts. And the placement of curb cuts is actually simpler than it seems at first. We have water running down through the parking lot, and we have our curb cut located so that the water would then run into our bioretention system. The thing that we have to discuss in terms of curb cut location is how far up or down this curb is the appropriate location for a curb cut. And the reason that becomes an issue is that where we've located our curb cut here, water clearly flows because the elevation of the curb cut, which is absolutely determined from the parking lot, the elevation of the curb cut is clearly above the low points in the retention area. We could actually locate that curb cut further up if we wanted, and water would still flow through the curb cut into the retention area. We could even locate it further up the hill if we chose, and water would still flow into the system. Of course, what would happen is that the area that's flowing into it would be a smaller area than the area that's flowing into it as we locate it further down. What we cannot do is locate the curb cut down below the retention area, because obviously the water is simply going to run in and go down the hill. So that's pretty obvious and easy. But the other issue is we have to be careful how far down in that bioretention area we locate the curb cut. So for example, if we locate it down here on the berm, the elevation of the curb cut, as I said a minute ago, is determined by the parking lot. So whatever this elevation is running this direction, let's say that's a 5.5, then we'd have a problem because we could not get the water to run back into the system because our high point is at 6.5 and the elevation out here is higher than that. So again, you have to go and make sure that your curb cut is located in a place that the water will run into your bioretention system. It will not run downhill past it and does not run into the berm. So again, let's go back and clean this up. Here's the curb cut. The curb cut elevation is absolutely determined by the existing parking lot elevation. We locate that curb cut so that the water clearly flows into the system and not downhill. Also note that there would be a drop in elevation right behind the curb cut where water could easily be dropping down. So for example, we have a curb cut here that is just shy of 6 feet, and our elevation in the bottom of this is down a few feet. And so we may want to add some sort of hardening, some sort of concrete or gravel at the backside of that curb cut to make sure that we're not causing additional erosion. But what's important right now is that you understand where to locate that curb cut. And the range that you have available is basically from the bottom side of the bioretention system up to the next area that you may want to divide. Now, once we have that curb cut in and we've got our bioretention graded, We also need to include the idea of a raised drop inlet. And remember, the idea of the raised drop inlet is it has to be below the elevation of the berm, because we want water to go into the raised drop inlet and not flow over the berm. So in this case, our raised drop inlet is at 5.8 and our berm is at 6.5. I also want you to note the location of the raised drop inlet, because that becomes an important issue. We want the raised drop inlet to be right after the curb cut. And the reason that we want that is that as the water flows into this bioretention system, it's going to start to fill up the bioretention system. Once that bioretention system is full, the water is going to take the path of least resistance. It's going to be coming down along this curb. It's going to run in, and the least path of resistance is going to be right into that raised drop inlet. The idea then, of course, is that we're assuming that it's dirty water that's going to be in the bioretention area here. And then once that fills up with dirty water, the clean water is going to go down into the raised drop inlet. So here we have the same drawing. We put the contours diagonally across the curve just for reference so you can see how they're connected. One of the things that we're trying to point out here is that the curb cut elevation and the raised drop inlet are related to one another. Again, you already know that the curb cut elevation is determined by the pavement elevation. The raised drop inlet is determined by two things. To begin with, it has to be lower than, at least a half a foot lower than the berm, but we also needs to be lower than the curb cut, because the idea is that as water fills up this system, the water then goes into the raised drop inlet and does not back up into the parking lot. We'll show another example where we do want to back up into the parking lot, and we may not need a raised drop inlet. But for right now, let's understand that if you're going to have a raised drop inlet, there are a couple of rules that you have to know about the raised drop inlet in terms of its elevation. First, it must be below the berm, half a foot. Second, it must be slightly below the curb cut. Third, the elevation between the raised drop inlet and the low points inside the bioretention system will determine the depth of water that you can hold within your bioretention system. So in this case, you see we have our low points at 4.5. We have our raised drop inlet at 5.8. So the difference between those two numbers is the depth of water that we can hold in our bioretention system. Now, another option that we have available to us that I want to make you aware of is a drop inlet. And that's simply a drop inlet in the parking lot. These drop inlets are normally made out of concrete, which costs more money compared to our RDIs, our raised drop inlets that can be made out of plastic. Now, in this case, we're kind of have a belt and suspender situation. We have water that runs down, it runs into, fills up, and then can overflow into the raised drop inlet. If that raised drop inlet got clogged, then the water, as it fills up, would block this entrance where the curb cut is. Remember, of course, that the curb cut is lower elevation than the berm, very important. And so as that water fills up this system, it will block this entrance, and the remaining water that's coming down will simply go directly down to the drop inlet. So this is a safety overflow, if you will, but as you'll see in the next slide, it also gives us an opportunity to eliminate the raised drop inlets if we choose. So in this slide, you see we have taken out the raised drop inlet, and that is a perfectly fine way to do this. What happens then is water flows down, it goes into the curb cut, the retention area fills up, it does not overflow because we have a berm that keeps it from overflowing. What it does is it backs up in the system, and then as it backs up, the water will block the curb cut. What happens, of course, then is the water cannot go into the system anymore. So the cleaner water simply goes down to the drop inlet. These two different systems, one where you have a raised drop inlet in the bioretention system, and the other where you have no raised drop inlet, but you have a drop inlet in the parking lot, are the core of what you're going to be doing for these systems. And again, getting the elevations correct is what makes this work, and we'll be talking about this a lot more. And then finally, we want to show what it looks like if we have a parking lot on both sides. We're not really worried about the drainage of the parking lot on the downhill side because it's flowing away. We're only worried about the drainage on the uphill side. And the contours, of course, will connect over, as you've already seen, in a fairly straightforward manner. So the system is basically the same, although we have this extra parking lot over here on this side. You're going to be designing the system for that extra parking lot downhill. So this is the sort of thing that you might have, a green median between your parking areas that you plan to use for your bioretention system. So now we're going to show you a typical example in a drawing of how this is done that includes all the parts that you need. We have the curb cuts, we have the low points in the parking lot, we have the high points that show where the berm is, we have the two contours, which you'll always have to have two contours here. We have then the water backing up and into a existing drain inlet. There is no raised drop inlet in this example. So we start on this drawing by having two curb cuts. These two curb cuts are uphill from the drop inlet. And it's important to notice that we actually label these, we can label them what we want, with one spot elevation, because two curb cuts going into the same retention area must be at the same elevation. Again, they must be at the same elevation, whether they're next to each other or not. You could have a curb cut on the opposite side of your bioretention, but if you have two curb cuts going into the same bioretention area, they have to be at the same elevation. The reason is really simple. If there was more than one curb cut and they were at different elevations, water would run into the first curb cut and out the second one. So let's imagine in this case that we had a curb cut up at this elevation. You already know that the elevation for that curb cut will be determined by the elevation of the parking. And so what would happen is water could flow into this curb one, and then it could be pushed out this one, or it could be pushed out this one. That defeats the entire purpose of trying to hold the water in the retention system. We want to hold the first flush, the dirtiest water, in the retention system and not allow it to flow out. So water coming across this parking lot runs along this curb and then flows into the system, right down this way and into the system as well. Even this direction, because then you can see that the slope is towards the curb cut. So all of this area is going to be draining into this bioretention system right here. And as all this water flows in, this system is going to start to fill up. It will continue to flow in, and the system will fill up a little bit more. And so eventually, the entire system is filled up, and this is what we have available for our bioretention area. Of course, we have our berm on our backside that keeps water from overflowing downhill beyond the capacity of the bioretention area. And then, of course, because we have this berm on the backside, this water backs up, and eventually it backs up to the curb cuts, and it blocks the curb cuts so that no additional water can flow into the system. So any additional water that's flowing across this parking lot, it has no choice but to flow to the corner and then into the drop inlet, because it's not allowed to flow into the bioretention area. So now we have a closed contour that basically represents the extent of the bioretention area. And I want you to note, this closed contour is running along the back of this curve. So it could be much steeper at the back of that curb much deeper than it would be on the front side of that curb. Berm, of course, is created between the two 1107 contours. That is the 1107 of the existing design and the 1107 for the bioretention system. You will always have these two contours adjacent to one another with a berm created in between in every one of your bioretention systems. It may not always be apparent, especially if you have walls, but this will always be true because you're creating a berm that keeps the water from overflowing the system. Students often get confused about how to do these contours. So what I suggest is you start by putting the contour that is behind the curb and looping around. And then you might be wondering, well, what is the elevation in case you've just drawn the contour? The elevation will always be the same as whatever contour is adjacent downhill. So you can actually draw these in ahead of time if you want. And just remember that the elevation of the two contours will always be the same, so we can have a berm in between. So these are the four basic parts that we always have to have in one of these systems. Start with, we have our curb cuts. Our curb cuts allow water into the system. We have a closed contour that may be running right along the back of the curb, as you know, and that is our containment system. We have two contours that will always exist, and they will always be the same in elevation, and that then creates an opportunity to put high points in between, and that becomes the berm that keeps water from overflowing the system. These same parts will exist in all of the retention systems that you design. So now that we've explained the basic parts that you have, we need to talk about the spot elevations that are required. And there are quite a few of them that you're going to need for each of these. First off, of course, you're going to need the curb cut. Those curb cut elevations come from the existing parking lot elevations at the point that you have the curb cuts. You're going to have the bottom points for the bioretention systems. You're going to have the high points for the berms. And then, of course, you're going to have a drop inlet in the parking lot, or you could have a raised drop inlet in the bioretention system. And we need to talk about how you set the elevations for each of these, because if you do not set the elevations properly, the system simply will not work. So here is your basic guide for setting the elevations for all of these spot elevations. You're going to need to come back and look at this quite a few times. It would actually be worth your while to pause the video at this point, take a screenshot of this slide for your reference later on. So to start with, we always start with the curb cut. You know that that is set by the elevation of the parking lot. That is a known elevation from the very beginning. You can then, if you wish, of course, set your drop inlet. That is also going to be known from the elevation in the parking lot. I would then advise that you set your low points. Those low points need to be at least half a foot to 1 foot below the curb cut. So the elevations that we're giving here are all in reference to the original curb cut. Once you have that curb cut, you can then determine the elevations for everything else. So again, the low points are half a foot to 1 foot below the curb cut. The high points need to be at least half a foot above the curb cut. Why half a foot? Because the way things are constructed is not that precise, and you do not want to leave wiggle room for someone to get it wrong. So the basic idea here, again, you always start with the curb cut. You then can set your drop inlet. You can then set your low points, and then you can set your high points. Now, when you set your high points, you may have to change some contours. So, for example, if this 107 contour doesn't exist here, or this one doesn't exist, you may have to add those. But these are the elevations that you will need for all of the spot elevations to make your bioretention system function properly. So in this drawing, you can see all the pieces that are needed. Again, we have our curb cut, we have our drop inlet, we have our low points, we have the contours, 2 of them, in a pair, always. We have the high points that create the berm, and these are all the pieces that you need. So now we need to talk in a little more detail about controlling the flow by setting the elevations within the system. What we've shown you so far is pretty simple and straightforward, but sometimes things get a little more complicated, and we want to show you the details of how this actually flows. So here we have a typical curb cut that you might find in a parking lot. It's sort of thing where water is running down, and it is then diverted into the system. And as this system, of course, fills up, water can then not get in, and it flows further down. There are a couple of standard parts that you'll see in this system, and that includes the cut itself that allows water to go in, the fact that there is some sort of a taper here on the sides, and it's important to have some sort of a splash block on the inside. It doesn't have to be made out of concrete, but it has to be something to try to reduce the erosive flow of water as it enters the bioretention area. And so here we have the same detail in section. Again, water is flowing in, and you'll notice that the splash block is down a little bit. It needs to be down because sediment and such is going to build up there, and that's one of the reasons that we have a little bit of stone back here to also help protect and control the amount of sediment. That splash block can actually put down further if you wish, but you need something there to control the erosive flows. And then, of course, as that fills up, water is simply going to spill out over and infiltrate into the bioretention system. So here we have the same sort of thing. The water is flowing towards the curb. It goes through the hole in the curb. It comes down and it hits hard. Notice this is a pretty big distance here. That could be, a foot or 2 if you wish. As long as you've got this splash block at the bottom to protect the system, it's going to work just fine. So again, just a fairly simple system where water flows in, comes down, moves into the bioretention area. And of course, it's going to slowly fill this area up. And even though we have the splash block down here, it could fill up much further if you wish. You can have that water fill up almost as far as you want. The difficulty is in what is a safe depth to have for that water. We're going to advise that you keep it at 1 foot or less for this assignment. And the next element to talk about is this raised drop inlet. You will have one of these in most of your systems, and we need to talk about the elevation for that raised drop inlet and the placement for that raised drop inlet. To begin with, in terms of elevation, we want it to be very close to the curb cut where water enters into the system. We do not want that raised drop inlet down at the other end of the bioretention system. We want it up at the top of the bioretention system. The reason we want it at the top of the bioretention system is we want water to come down, hit the edge of the raised drop inlet. It's simply then going to go around the drop inlet. At that point, it's going to start to fill up with water. But because it is at the top of the bioretention system, any other water that comes in will go into the raised drop inlet. And so the polluted water that's down here is not resuspended into the raised drop inlet. It's only the clean water that comes in later in the system that goes down into the raised drop inlet. So here we have 3 typical designs, and these are designs you might use in your project. So we've got water running across the parking lot, drops down and hits the splash block, and then the system starts to fill up. And the second one, of course, is running across the parking lot, comes down, hits the splash block. This allows greater volume because you'll notice that we made this one deeper by changing the slope after the splash block. And of course, here we have one that has a wheel stop Bit of debate about how well these work to be truthful, but the basic idea is still the same. Water goes, and there's no need for any sort of a curb cut here because it's simply a small retaining wall that allows the water to go down into the bioretention system, and then the whole thing again starts to fill up with water just like the other systems. So when we add the raised drop inlets in, the system still basically works the same. Water goes into this system. The system starts to fill up, and once the system is full, the cleaner water that's coming later goes directly to the raised drop inlet and is discharged. Same sort of thing with the second one. Water comes in, it flows down, it goes past the raised drop inlet, it fills up. The cleaner water that's coming later goes directly into the raised drop inlet, and on the last one, the same sort of thing. Water flows in, the system fills up. The cleaner water that's coming later goes directly into the raised drop inlet. So you've got a couple of things that happen with these raised drop inlets. By changing the elevation of the raised drop inlet, you can control a couple of things. First off, you can control the volume of water that is held. And so each of these has a different volume of water. You can obviously control the depth of water in the same way on all three of these systems. So these are three simple, straightforward designs, but you need to be aware that the challenge comes by what happens at the other side, that is down at the other side of the retention systems. That's where a lot of people have difficulty because they're only focusing on the curb cuts and the raised drop inlets, and they're not focusing on what happens at the other side of a bioretention area, whether it is a berm or more challenging if it is a curb or the other part of the parking lot. So here we have three examples that have all caused a problem or a challenge for us, if you will. On the top one, the level of the water, and again, the level of the water is determined by the level of the raised drop inlet. The level of the water is too close to the top of the curb here. So unless this is built very exactly, water will overflow. In the second example, the water is already above the curb. So the water is going to flow over the curb into the next parking lot before it flows into the bioretention system. And in the third example, this is even more extreme. The water level that is set by the raised drop inlet is much higher than the adjacent parking area. So the whole system is going to overflow into that adjacent parking area, and it simply will not work. So we're going to address these one at a time. In the first one, we have the water level that is too close to the top of the curb, and so water is going to flow over. To solve that, we need to change the elevation of this drop inlet so that it is not as close to the existing curb level. So all we had to do was lower the raised drop inlet so that it was 6 inches below the curb that is downhill, and that then holds the water level where we can control the flow in and out of this system. And in the second one, the solution is the same. We've simply lowered the raised drop inlet so that the water level is well below the curb that is downhill of the bioretention system. This third one, however, is a little more challenging. We just lowered the raised drop inlet, but we haven't lowered it enough to keep it from flowing over. So of course, we have two options that's available here. One is we can lower this raised drop inlet even more if that solves the problem. But another option that you may have to use is you may have to raise the land to create a dam before you get to the existing curb downhill. So you've got two choices here. One, you can definitely lower the level of the raised drop inlet, but two, you can raise the level of the land over here to create a berm so the system does not overflow. All of these are available for you as designers to help make this system work. What this means, of course, is that you have to have a lot of spot elevations to make this function. You need the spot elevation for your curb cut. You need the spot elevation that is for the splash block. You need the elevation that is for the raised drop inlet. You need the low point. You need the high point, and you also need the top of curb for the next parking area. In the second example, same thing. You need the curb cut elevation, splash block, raised drop inlet, low point of the retention area, high point of the retention area would act as a dam, and the top of curb for the adjacent parking lot. And of course, in the third example, the exact same thing. All of those points are going to be needed in order to explain how this system works. So quite frankly, this is a lot of spot elevations you have to put in. We're going to point out again the most critical one. The berm has to be half a foot above the raised drop inlet. If the berm is created by a curb, then that curb has to be half a foot above the raised drop inlet. The raised drop inlet needs to be below the curb cut in all cases, and the bottom, the low point, needs to be defined so that we know how much water is going into and being held by your bioretention system. I'd advise you go back and look at the slides that give those specifics again, and then we'll go into more detail in the next lecture. So again, this third lecture is about how to grade your retention systems. It is an introduction to this. Be aware there is another lecture, number 4, coming up that you are going to need to look at in order to understand how to do this in more detail. We would advise that you go through this lecture probably twice and then start looking at how you're going to grade some of your retention areas, and then we'll have another lecture for you to give you a little more detail for special situations, which most all of you are going to need to know about.